Yo, fam, it's about time we talk about reverse engineering at a deeper level. Really quickly, if you're new to reverse engineering, go check out my video Reverse Engineering Part 1 and then take a look at Part 2 as well. You can see some basic examples and understand how reverse engineering works at an overview or like a surface level. But now we need to talk a little deeper about reverse engineering. From this point forward, things are going to get a little more complex, so I'll break down the videos into little chunks. If you're new to this channel, make sure you subscribe. It helps me out a lot. Like the video, comment what you'd like to see below, any questions you have, and I'll do my best to respond to those comments. And if you're not new, well, make sure you comment and subscribe to this channel. One thing in reverse engineering that you'll commonly come across is encryption. Now, encryption being things like, we'll say encoding, you can say hashing, or just encryption with some kind of key. In reverse engineering, that looks a little bit different because now we're talking about the assembly level or like lower level code. And usually that's manifested in many ways. One of the most common that I've seen is utilizing arithmetic logic. So for example, let's say we use XOR, which is one of the logics that can be used. There are others. There are things like AND, there's like OR, and there's just, a list. There's a bit shifting, there's a list of things that you could do. Let's say this was XOR, this specific type of arithmetic logic. In assembly language, one way to actually encrypt a word, we'll say, is to take each letter, run it through an XOR operation, and then get the output, which would be a new letter, and then run that through the rest of the code. So if we have something like A, B, C, we would take A, we would XOR that with, we'll say, a number, and that A would provide a new value. We'll say the value is L. Then we take B, XOR that with a number, and that new value comes out, maybe it's M. And lastly, we can take C and XOR that with a number, and maybe that comes out as N. That's how encryption could work. That's just one of many ways. In this case, if we are utilizing encryption in this manner, the value that the input is being XORed with, we'll call that the key, the encryption key. And you can use this sequence, run it through backwards or reverse the sequence to understand how encryption is working. But you can also use this to find common things like password cracking. You can find what the true data is as it's been obfuscated. So if you're reverse engineering malware, sometimes the actual strings will be obfuscated, and you can deobfuscate those strings when you reverse the arithmetic logic. Sounds complicated, but bear with me. We'll look through this. We'll do some examples so that you can see. But before we start looking at the examples on arithmetic logic, let me explain a little bit about what that logic is, and then let's do a little bit of math so you can see how that looks. So when we talk about bitwise operations, there's a few operations you need to know, and we'll go through them right now. So there's AND, the AND operation. Say AND. There is OR, the OR operation. There's the XOR, which we're going to be focusing on for this video. There's NOT. There's NAND operation. What's that? It's NAND. There's the NOR operation. And there is the XNOR. These are the basic type of operations that we are going to be looking at with assembly. So in this case, you would be, we'll take and then we take two registers, or we'll take maybe a register and a value, or maybe we'll take a pointer and a value. But essentially what you'll do is you'll take some value and you'll run the bitwise operator. In this case, it would be and you'll run that with whatever the initial value is. I'll show you what I mean in a second. I put up a link to the table on all the bitwise operands and the math behind all of it in the description. I'm not going to go through all of them. What I will go through is the XOR operation, because that's the operation that we're going to use for the sake of this explanation here. So when we're looking through assembly code, you might come across, as I mentioned, some kind of encryption. One of the most common that I've seen is XOR. And in order to understand what's going on there, it's probably easier to do it by hand first. And then I'll show you how it looks on the debugger on the computer end. So let's say we have some address. We'll say a DDR for address. And we'll say that address is XORing something. So that's going to XOR. And we want to XOR, we'll say, a value in a register. We'll use EAX, which is a 32-bit register. And we want to XOR this value inside of EAX with the hex value, 0x 54. There. You come across a line like this and you want to understand what is going on. So bitwise operators, as it sounds, it has to convert things to bits and then do some kind of operation. So in order to do that, the first thing we need to do is convert these numbers into bits so that we can perform an operation on those bits. But before we do that, we need to figure out what's inside of EAX. And then we need to convert this, both the number inside EAX and the hex number, to binary. In this case, for EAX, we'll say if we want to know what's inside of that, we'll say there's a hex value of, we'll do 0x, I don't know, we'll say 72, just like that. Now we have 0x72 being XORed with 0x54. We'll say that. So the first thing we need to do is convert it to binary. And to do that, we actually take 8 bits. So we can do 1, 2, 3, 4, 5, 6, 7, 8. And then each bit has a place. So this is the ones, this is the twos place, and then we just multiply by 2 here. So that's 4, this will be 8, 16, 32, and 64 and 64 and 128. There you go. So in order to actually convert this to decimal format, we first need to convert the 5. And then, so we take the 5 and we convert that to a 4 digits binary. So four bits there. And then we take the 4 and then we also convert the 4 into 4 bits. So starting with the 5, all we actually have to do is add up the places and toggle the zeros in order to get to the 5. That's the way I do it. So for 5, we have 4 plus 1 equals 5. So if we toggled this 4 and toggled the 1, that would be our value. And we're only doing 4 digits, so I'll split this in 2 here. So we're only doing 4 digits here. So we don't actually need this side for the sake of this demo. We don't need this side here because we're just dealing with the 4-digit hex because we're splitting them into 5 and 4. So for this, we have 4. So it's 0, 1, 0, 1, which is because we toggled 4 and 1 on. So 5 would be 0, 1, 0, 1. And then for 4, we just toggle the 4 to get to 4. So that's 0, 1, 0, 0. So that would be 0, 1, 0, 0. And that's our full binary for the 0x54. Now we do the same thing for 0x72. For this, we toggle the 4, we toggle the 2, and we toggle the 1. So 0, 1, 1, 1 would be 7. So 0, 1, 1, 1. And that's our 7 here. Now we have to go and get our 2. And our 2 is going to be just toggling on the 2 here. So 0, 0, 1 for the 2, and 0. So 0, 0, 1 for the 2, and 0. Now we're ready to do our XOR operator, now that we converted both hex values to binary. So to do that, we know that XOR, if both numbers are the same, then it's a 0, otherwise it's a 1. So 0, 0 would be 0, 0, 1 would be 1, 1, 0 would be 1, 0, 0 again would be 0, 1, 1 would be 0, 0, 1 would be 1, 1, 1 would be 0, and 0, 0 would be 0. So our final value would be this number here if we were to do an XOR operation on this. Now, binary doesn't really do much for us, so it's probably better to convert this to either hex or decimal format. We can do either or. So to convert it by hex, all we have to do is split it up again. There we go. So we can split it up and we can say this is the 1's place, is the 2's place. So that's a 2, and that would be 2. And then this would be 2's place, this would be 3's place. So this would be 2, and the next one would be not 3's place, sorry, this would be the 4's place. So that'd be 4. So this would be together 6, not 2. So let me just take that away, and that would be 6. So together we can say this is 0x26. Now, we could also convert this to decimal format by just adding it up together. So if we do 0, 0, 1, 0, 0, 1, 1, 0, and we know that's the 1, 2, we'll just toggle the ones that are on. So that's 4. This is 8, 16, 32. All right, so 32 plus 4 plus 2. We don't need this 1 because that's a 0. So this would be 32 plus 4 is 36. 36 plus 2 is 38. So if we want to convert to decimal, this number would end up being 38. And so that's how you would do the calculations, but also conversions. So this is hex, and this number would be decimal. Now, this is a lot of work to do, especially if you're going to be seeing a lot of XORs and other bitwise operators to convert it to binary and then convert it back to hex and decimal. So it's probably easier to use something called an ASCII table that has the hex value that corresponds with the decimal value that corresponds with an actual letter. Because for example, if we have a decimal, if we have the number 10, right, that would be 0xa0 for hex, right? Because 10 represents A for hex. So there's an ASCII table that actually will go through and do this and show you the conversions here, which would make it a lot easier. But just so you know, in order to develop your own table or anything, if you want to convert from decimal to, if you want to convert from binary to decimal, you add them all together. If you want to convert from binary to hexadecimal, you split it up between 2 4 bytes, and then you combine those bytes at the end and you get the hex value. That's how you would do that. All right, we just did XOR by hand, and you know these two. So if you wanted to grab the XOR, that's 38. And that's the hex value for it if we want to XOR. So we know how to do it now. Let's take a look at a practical example using some kind of like debugger and seeing how it looks there.
Okay, so this is a Kali box that we're going to use to look at a semi-real world example. So I created an application that basically will just validate a password. So the way it works is that the application stores the actual password encrypted, and then it uses a decryption key to decrypt the password, and then it matches that key with whatever your input is. And if it matches, you get a flag. If it doesn't match, then it'll say invalid password. So that's the way it works. And we're going to step through it with GDB, the new debugger, just because I've been using this for some time recently, so I'm just more accustomed to using it. But you can use any debugger like IDA Pro, we can use Cutter, we can use Ghidra, any of those debuggers will work, and this is a relatively easy application I just set up just to show you how to decrypt something that's using basic XOR encryption. Also, the way that the XOR encryption works is that it is encrypting each character instead of a full word. So if the password happened to be test, it will take the T and XOR that with the key, and then take the E, XOR that with the key, S, XOR that with the key, and T, XOR that with the key. Each character is converted to hex, and then it's XORed with the hex value. So very similar to what we just did in the example. Okay, so to start with GDB, we want to first look at main. So to do that, we just type in disassemble main. That's what we can do. So really quickly, before we actually dive into main, one of the things that GDB likes to do, or GEF likes to do, is not give us the full address of the functions that we need. So in order to actually load the proper addresses, we actually need to run the program once. And then I'm just going to type in random password. We'll see access denied, invalid. Okay, now that we did that, we can go back to the disassemble, and now we have our addresses loaded. Okay, so reading down here, we have our base pointer, we have a stack pointers here. Really quickly, when you see things like RAX, for example, that's 64-bit. I think I mentioned that in the part 1 video. EAX is 32-bit, which part 1 pretty much goes over. But whenever you see an R, it just extends EAX. So it just becomes a 64-bit register. There are actual assembly, I guess you can call these actions, assembly actions that will extend EAX and make it RAX. And I think we might actually see that later, maybe. But if you don't see any actual function that will extend EAX, then you can just assume that, RAX, the R here is 64-bit. That makes that register 64-bit. Okay, so let's step through. We see some basic functions here. We're calling this function a print function at this address. And then we're calling another built-in function here. So anytime you see like this @PLT, these are pretty much built in for GDB. And then we see one here that looks like a custom function. So this is an interesting one for the main, because main calls this function, and this is the only function that we see that's relatively worded in a way where, well, yeah, we probably want to see what's in check password, because it's probably loading our encrypted password to do some kind of check. So we're actually going to go into that. So to do that, we want to go into our disassemble, but this time we want to type in check password. Here we go. So this is our check password function. And we're going to step through it and see if we can find the proper function that we need in order to grab the encrypted password and also the encryption key so that we can decrypt that password. So let's step through it. So we start at the top. We see here, we're pushing our pointers here. And then we're moving the whatever value is in RDI to a keyword pointer. We'll keep moving down because we're just moving some values around. So now we're moving values in this pointer to our 64-bit register RAX. Then we move RAX into RDI, and then we call, this function. We'll keep moving down. What I'm interested in is looking for some kind of comparison or something like that. So if you keep moving down, we see a jump, our first jump, which is great. So our first jump is jumping to this address here. So we're going to take a look at this address really quickly. Before we do that, I do want to point out with GDB, you'll see something like check password. Well, in this case, it'll be a function and it'll say like plus something. So if you see something like this, that's basically saying that this is 70, like you're adding 70 to the check password. So this address here, if you subtract 70 from this address, then it will equal the check password function. So that's basically how that's working. So in this case, we're not, we could look at the check password directly from here by just subtracting 70. But we're going to keep stepping through and just see, just because we want to make sure we understand what check password is and what we're doing. So this is ending in 1CF. So we want to go down to the 1CF, and we see that right here. So now we're in 1CF. We see, again, we're moving a pointer into our EAX, which is a 32-bit register. But then from there, we're comparing what's in the 32-bit register with another pointer. So we're basically comparing this pointer with this pointer, which is interesting. And then we have a JL right after the comparison, and that JL is moving to this address, which is 36 spaces, well, 36 plus the check password function. Now, JL is a jump conditional, so jump if one value is longer than the other. That's what the L is for. So it's pretty much saying this pointer, when comparing it with this pointer, if this pointer here, the first pointer, is longer than the second one here, then we want to take the jump. And we're going to jump to this address, which is 1AD. In this case, we don't know. The way we would find out is to set a breakpoint, and then we would compare two values, which we can do. So what we'll do is we'll just type in break, and then we'll come back to that breakpoint. We want to break at this comparison right here. So we want to break there, and we'll copy that, and let's paste just like that. So now we have our first breakpoint, and then we'll compare that. Let's assume that it is greater and we do get our jump. So in this case, we're going to jump to 1AD, which is right here. So now we have moved here to this section of this function. So now we're moving a pointer into EAX, so we're overriding EAX after the condition. And then we see this CDGE. So this is actually just an extend function. So whatever happened before it gets extended. So in this case, EAX, which is 32-bit, would be extended to 64-bit, effectively making it RAX technically, but it can still be called as EAX. It's just extended. From there, we're doing an LEA function, which is just shifting. So it's just a shift and add. So just shifting some of the values and adding something to these values. So just, the address here or the register here is just being moved inside RDX pretty much. So the pointer to this value here is being moved to RDX. And then we have a move and extend. So we're moving this pointer here to this register, and then we're extending that register as well. So we're extending to this register. Okay, from there, we're doing an XOR. So here, we should have some kind of value here, and we're XORing that value with 0x54. And then once we XOR that value, we're moving our XORed value into EDX, and then we're adding another, in this case, another, pointer reference to EAX. And then from there, we're extending it again. And then we pretty much go on a loop, right? So then it's moving down the line, and then we hit this jump if greater than, right? And then once we hit the jump if greater than, it sends us back up here. So this here is our loop. And it looks like it's just going to keep looping until we go through all the characters of the encrypted password. So in this case, we see that GDB actually comments where the encrypted password is. That's something that's a feature of GDB or GEF. So it's also a feature of other debuggers. So IDA Pro, Ghidra, Cutter, you should see something like this. It'll try to look for that value. And it is basing it off of things like this, right? So check password plus 70. If you subtract 70, you actually end up with the correct check password address. So it can easily find that. We could have found that ourselves. So because we see that, we also see down here the XOR, and we know that this is the only XOR. So, and we know that the encryption type is XOR. So we can see that each value is being XORed with 0x54. So this is our XOR key, 0x54, just from the example before this. So we should assume that, EAX is taking a character, is XORing it with 0x54, and then we get our actual value. And we could set breakpoints just to try to figure out what's going on here. So we'll set a breakpoint. Well, we could set it at this XOR, just so we can see what's being XORed here. So let's do it. So breakpoint at the XOR, and then we could do we have the breakpoint at the comparison. So this should be fine there. And we'll set the breakpoint there, and we'll go from there. So let's run, let's enter password. We'll just do ABCDEFG, and we should hit our first break, which we do. So our first breakpoint is the comparison, which I mentioned, the EAX, the word pointer. So we can take a look at what's in both. So to take a look at what's in EAX, we're just going to do a simple print statement, and we're going to print. So right now, looks like there's 0 in EAX, and then let's look at this pointer here. So to look at this, we want to do XS, and then we'll grab it like this. I think we need to put a $sign. There we go. So we just have /A there. So we don't actually have to put XS. We can do 32-bit. So we'll do 32GX. and we can see hex values that are in here. So if we match the address here, which this is just we're looking through at the pointer here. So if we match it, we see this hex value, which is just 0x07. And this is also little endian, so we read that, backwards. So in this case, it would be 0x70, 0xdd, 0xff, so things like that. And these are appended, so these are together here. So that's how that is. So this value is definitely greater. I might have actually said that backwards earlier. If this value is greater, then this condition should jump, not the top one here. But so this bottom value is greater. So we're actually going to jump to the 80, which is fine. That's exactly what we want. So we're going to continue. All right, now that we continue, we are stopped again at our second breakpoint, which is the XOR. So let's take a look in what's in EAX, and then we'll go from there. So we can do print EAX. Okay, so we have 0x19. Let's see if we can get the actual value. No, well, at least I don't remember how to do it. So that's fine. We can grab that later. I'll do it all together. So we can assume that basically what's happening is this is our non-encrypted value. So these are the letters of what our password would be, and then it's encrypting it with 0x54, and then we should get the encrypted value once we continue. So let's do this. We're going to set a breakpoint just so that we can see what that value becomes after the XOR. Boom. Okay, so now there's another breakpoint, which is right here. So you can see what happens after it becomes an XOR. So this value is also the first value of our password. So theoretically, if we set a breakpoint and we keep going through this loop, we should get all the characters of our password in plain text. So we shouldn't have to reverse this XOR. But for the sake of this demo, might as well reverse the XOR. Okay, so now that we set our second breakpoint, let's continue. And we hit our second breakpoint here. I really want to see what's in EAX. So let's take a look at EAX. Boom. So there we go. So it was 0x19, but now that we XORed it with 54, now it's 0x4d. So our first character should be 0x4d. And as I mentioned, if it kept looping, you can just look in what's in EAX, but we're going to focus on the encrypted value, and we can always reverse that. Okay, so now that we know that this is part of the XOR encryption, we can move upward, so we can backtrack, right? So we have going up back to our XOR, we have EAX somehow has this value. Let's see where it got it from. So right before this XOR, EAX was assigned the value of this pointer, RAX plus RDX plus times 1, which means that this value contained our this pointer here. So this pointer reference contained the character that we needed for EAX, which then passed it down here, and that was where the XOR happened. So we know that our RAX plus RDX plus 1 times 1 has it, but we need to figure out what address this might be at, right? So if we go at 1, we can see RIP plus 0 plus this address here is equal to RDX, and so this RDX is directly tied into here. So we can probably take a look at what's in this RDX when it's down here and see if we can figure out some kind of pattern. So let's print that, and we get an address, which if this holds an address, that means there's some kind of word that is probably part of our character sequence, considering that RDX plus RAX, times 1. So just taking the first value of RDX and plussing it with RAX, so adding that. So in this case, it should be getting one character, right? So whatever's in this case, whatever's here in EAX, it's moving it one space and then just grabbing one character kind of thing. So this address should have all the characters together. So we can look at this address, and let's do that. We can do hex dump, and then we can specify this address just like that. Let's do like that. If I can get it right, let's do byte. See if that works. There we go. That works. Before we do that, actually, let's see if we can just uncover this in plain text. No. So the XOR is causing some kind of obfuscation, so the debugger can't read the plain text password. But that's fine. We can still look at the hex dump. Actually, I'm going to look at the hex dump a little bit in a little different way, just because it'll be easier to read. So we're going to do x/, and we'll do 32, and then we'll do gx. We'll look at it this way. Okay, this is a lot easier to read. So we see in our first line here that this address that we had is the address of the encrypted password. So this, theoretically, this should be our encrypted password, which is good. This is exactly what we need. So what we'll do is we'll copy this, and we'll do notes.txt. We can just do a sudo vim. There we go. And we can paste that there just so that we have it. Now, really quickly, this is little endian format. So when we read these hex values, we're reading it from right to left. So it'll be, technically, if we split this up into each character, it's 0x19, 0x2d, 0x07. So that's how you read it. And then these get appended to the end. So 0x65, 66, and 67. So that's how we read it. So assuming this is our encrypted password, And we did see that if we look at the XOR function, we're XORing with 0x54, meaning this is our key, 0x54. We actually have everything we need to decrypt this function here. And so in order to do that, all we have to do is XOR the encrypted value, and we should get the original. So in order to reverse an XOR, you just XOR it again, and then it'll reverse that process. So we can actually do that we can use a Python file, xor.py will do. In this case, we're gonna create a list, and we'll just iterate through the list here so that we can see the output of this encrypted value in plain text. So in order to do that, we'll do a val1 for all the first set of values, and I can do open bracket here. And I just want this set of values here. Boom, just like that. And then I want val2 for the second set. And the reason why I'm separating them is because with these leading zeros, we actually don't need to copy these zeros. In fact, these will just be extra characters for us because it'll XOR these zeros as well. And that should come out with whatever character 0 XORed with 0x54 would be. So we don't need that. I mean, this is going to be 0x, and then I'll paste the values here. There are other ways you can write it. So I can write it like 0x19, assuming it's little Indian, I can have the list go 0x, the next value would be 2D, and then go on each character like this in the list. And then I can have each character XORed with 0x54. That's going to take too long. It's easier to just kind of dump it in as one long hex string and then separate them as you go. At least that's what I find to be easier. So let's go ahead and separate them, as we said. So we'll say for V in val1, yeah, that should work. For V in val1, we'll say string. We want to see the string, and the string will be equal to v dot 2 bytes. So we want to convert them to bytes in order to do the conversion. And oops, we need an underscore there. And we need to count how many bytes there are total. So two of these are equal to 1 byte. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 total. So it should be 16 total numbers and 8 total bytes. So 8, and then that's we want the byte order, and the byte order is little Indian. That's the order that I set it to, so we know that. All right, so now we want to do V again, and so this time we actually want to print out the values. So we can do, actually we'll do for B in bytes. So for all the bytes that we have, we're gonna do for B in bytes. We'll do for string. So we'll do for char and string. That makes things easier. Char and string. There we go. We're going to then assign. We'll say C. C would just be the character, and the character is going to be equal to CHR, and that's going to be char XORed. So in Python, you can use this uproot here, the character, which is exponent, as XOR as well. It works in the same way. And that's going to be XORed with 0x54. Okay, so now we can pretty much copy this and just change some values to match with the second list. Let's paste. Oops, let's go to here. So let's copy that and let's paste. I guess it doesn't want us to do it. That's fine. We'll just type. So again, for V, and this time we're just going to do val2, and then string is equal to v.2 bytes. And then we need to count the bytes this time. So this is 1, 2, 3. So that was easy. 3 bytes. Byte order equals little. And then for each char in the string, we want the char equal to CHR, and then that's char uproot 0x54, just like that. Boom. Okay, so now we're just a step through what we're doing. What we're doing, we're saying for all the values here, we want to do is convert these values into bytes. And then for every character in each byte, and since we set the byte length to 8, it knows 2 bytes equal 1 character. So that's the way it's working. So for every character in a byte, XOR every character with 0x54. So in this case, it would be 0x19 XORed with 0x54, 0x2D XORed with 0x54, and so on and so forth. And we did the same thing here. So now that we actually did that, we can print out the values. So we'll just do it all in one print. So we can, in this case, we can print out, well, we can print C, but what we'll do is this. We'll kind of separate them. There we go. And just to make this a little more differentiatable, we'll do V2, and then here we'll do V1, just to be able to differentiate the two, and that's going to be C2. All right, so now we just print C1, and we can also add that together with C2. There we go. And this should now print as characters in like a string format, and then we just put the strings together, and we get our value. So that's that, and we'll Python XOR T3. Let me see what I might have missed here. Oh, let me do string 1. That would be smart. And then this will be string 2. I might have to actually move the print statements to the inner loops here. So that's string 2. This is string 1. Yeah, so I might have to. So let's do it like this. Instead of moving this to an inner loop, what we'll do is we'll just have it as a one-liner. It'll make things a lot easier. And that's for, we'll say for char and string 2. And so this now makes it like a one-liner here. And then same up here. That way it avoids the extra looping. It's a similar thing, but just to avoid. So char, we'll say char 1 or char 2, string 2. There we go. Now we want to print C1 and C2. I see the issue. So actually there's a couple of issues here. So I converted to one line. I actually didn't even need to convert it to a one-liner. So it looks like the value that I'm XORing here is saved in this char variable. But when I started the loop, the one-liner loop, I put char 1. So I either need to add a 1 here or remove the 1 there, but I'll add the 1. For char 1, I actually need an n right here, in string 1. There you go. And then the same here, char 2. So I actually didn't even need this join technically, but it's fine. I'll leave this join because it will join the letters together to make it more readable for us. Okay, let's try this and let's see what happens. There we go. Okay, so now we XORed each letter and we join them together. We get them as a value. So now we have the decrypted value, and this decrypted value should be what our actual password is. So we can test that by, first I want to remove the breakpoints. So I'm going to just write info breakpoints. We have 3. We have breakpoint 1, 2, 3 that we already hit once, and this is going to loop until we add all the characters together, basically. So that many loops, and we don't want to do those loops. So we're going to delete these breakpoints. Delete 1, we'll delete 2, and we'll delete 3. Then we can look at the breakpoints you see, no breakpoints here. So now we're not even going to continue this. We're just going to rerun it from the start, and then we'll type in our password. That was it. My secret, 1, 2, 3, enter. And it says, access granted, welcome to the system. And then we get our flag here, that just our made up flag that we get. So we figured out the encrypted password, just a recap. We figured out the XOR key, which is here. And then we encrypted each letter and their hex value to the XOR key. And then we technically do get the XOR hex value, but essentially we converted that to string. And so we get the string part of that. If we wanted to actually see the hex value of it instead of the string, then we could change the CHR. So we can do something like this. I think it's hex, hopefully, can't remember, but let's see. All right, we'll try that and we'll see. Yep, so that works. All right, so now we see the hex values. It's a little weird because it's all kind of together and individual. So let's remove the join for the hex values here. Okay, so now remove the join. We can run it again. Did I make a typo while removing that? Yes, I did make a typo. Because I removed the join, I think I need to add the brackets here. That should work. Yep, okay, there we go. So now we see our each individual value. So this is our actual password that's decrypted from the XOR. So again, we will combine these. These would be individual. And then if we read it backwards, right? So 0x19 XORed with 0x54 should equal 0x4d. And I think we saw that earlier while we were looking through the assembly. You're gonna let us scroll up that. There it is. So when we were printing the EAX register, we see 0x4d, which is accurate. That's our first encrypted character. So that's how that works. Okay, thanks for watching. I hope you learned a little bit today, especially with encryption and how to decrypt a lot of the stuff with assembly. You're not going to be able to decrypt everything, but it is worth taking a look at how decryption is happening and if there is a decryption key that's able to be dumped in the disassembler. And if you can, then you can very much likely reverse the process utilizing that encryption key. So if it was XOR +2, I don't know, shift some bits to the left a little bit, and maybe an AND, well, you just do that in reverse, right? You can AND -2, shift some bits to the right, and then XOR, and that should reverse the password. So that is how you check for password encryption. You figure out what's going on. And if you made it this far, thanks for watching the demo. Hope you learned something from this. When I first got into reverse engineering, it definitely wasn't a cakewalk. So
The way I learn is by literally going line by line and trying to figure out what a function is doing. When I see move EAX 0x21, what is happening? When I see a CMP function, which is compare, when I see a JMP, a JNE, a JE, any kind of jump function, what are they doing? And I would comment line by line. It was a tedious process, but that's helped me to learn. And so if you're trying to learn reverse engineering and get better at it, just like with anything, just like with fighting, just like with speaking, you need to practice at it. That's my best advice for you. Take it day by day. Don't skip over any of the basics. Go back. I spent a few months just learning what each of these functions meant and what they did. And there's still some functions I don't know. And I have to Google it. So make sure that you're taking your time, you're learning how to do these things before you just jump into reverse engineering. I'll keep making videos about this. I'll try to push them out more frequently instead of having this gap. But more importantly, let me know what you'd like to see or any questions you have in the comment. And don't forget to subscribe. I'll catch you guys in the next one.